My talk is based on the joint work with Ivan Vinnikov, which is now published on Archive. And the talk consists of three parts. In the first part, I introduce convex surfaces in the sense of Giroux. Second part, I introduce rectangular diagrams for convex surfaces and surfaces in general in the free space. And last, I will discuss some problems and results. So, let M, definition. Let M be free manifold, oriented and closed. By a contact structure on M, we call two-plane distribution, two-plane field, which is specified by one form. And there is a restriction on this one form. This non-integrability condition. If for some one form alpha the following holds, then it is integrable. This means that there is a two-dimensional foliation of the three manifold, and each leaf is tangent to one form. So the kernel of one form is the tangent plane to leaf. And our condition is non-integrability. So this is a volume form multiplied by some positive function. So this is a contact structure. Contact structure. Example. R3. Take the form dz plus x dy. It is to check this contact structure is called standard contact structure. Xi standard. Or equivalently, you may take S3 in two-dimensional complex space and take in every point take a tangent plane to a sphere and intersect it with the image of this plane under the multiplication by I, the operator of complex structure. This is a field, two-dimensional field in S3, and it is a contact structure. If you remove one point from S3, then you obtain R3 with the same contact structure, with standard contact structure, by some change of coordinates. So this is almost equivalent contact structures. In general, there is a problem classification of all contact structures on the given three-manifold. It is known that in every homotopy class of two plane fields, there is at least one contact structure. It is also known that in every homotopy class of plane fields, there is a finite number of contact structures. But for every three-manifold, it is some problem of classification. For example, if you take S3, then in every homotopy class there is one contact structure, but in one homotopy class, trivial homotopy class, there are two contact structures. One of them is psi standard. So for S3, the classification is done. Convex surface. Suppose the surface is F is embedded in contact manifold, and there is a vector field that is transverse to this surface. Surfaces will be closed in my talk, but they may be with boundary and they may be non-oriented, but for simplicity they are oriented and closed. A vector field that is transverse, and this vector field is contact vector field. That means that the flow of this vector field preserves the contact structure. Say my form is alpha, so I denote by phi t the flow of vector field V. So this holds. Or equivalently, the Lie derivative of one form alpha is this form multiplied by some function. This notion of convex surface was introduced in work of Giroux in 1991. And all elementary facts about convex surfaces in my talk are proved in this work. Okay. Yes, I forgot. Surface F is convex surface. Convex surface. M is a contact manifold. F is a convex surface embedded in contact manifold if there exists some vector field which is transverse to the surface and is a contact vector field. Its flow preserves the contact structure. Locally, every surface is convex. Let's consider some models for neighborhoods of points. Suppose in some neighborhood of point on the surface, your contact structure is simply dx, where x, y are coordinates on the surface, and z is the transverse coordinate. Suppose your form, is simply dz plus x dy. And in the neighborhood x doesn't equal 0. Then the contact plane is transverse to the surface in each point of the neighborhood. So the fluctuation that you see is linear. The vector field, take the vector field d over dz. This vector field obviously preserves this form and our contact structure. So locally our surface is convex. Let's take some singular point of the surface. This surface is locally convex. This is neighborhood of some point P, and we
so that's the xy plane.
yes, xy plane, yes, and we find the vector field which is transverse to the surface, and the conditions are satisfied. Okay, take a single point. Now the form is dz plus r squared d theta. R theta are polar coordinates on the surface, and z is the transverse coordinate. Then again, you can take the vector field d over dz, and locally our surface horizontal plane is convex. It may be a saddle on the surface if locally our form is, for example, dz plus x dy minus 2 y dx. This is I draw a fluctuation on the surface. I draw, so just intersect the tangent plane to the surface with contact structure in every point. So generally you see this picture, just linear foliation, and when the contact structure is tangent to the surface, the foliation may look like this or like this.
So if you write minus y dx, what's...
This is not contact structure, maybe. I don't remember. No, the foliation will be different. The foliation will be not so. The singularity will be not general, will not be general. Not generalizable. Okay. So, okay. The theorem of Giroux is that the condition that the surface is convex is general. So, every surface may be slightly moved smoothly, and it will be convex. Convex surfaces are general. Generic. Sorry for my English. In the suppose there are two convex surfaces, and we try to distinguish their neighborhoods. The question: F1 and F2 are convex. Consider the neighborhoods as contact manifolds with the induced contact structure. Are they different or not? That is the question. Neighborhoods as contact manifolds. And Giroux gives a simple answer. One more definition. Gamma, the set on the surface, let F convex surface, let gamma be the set of points where contact vector field lies in the contact plane. Yeah, F convex surface where V contact vector field which is transverse to the surface, and gamma is a set of points where this vector field lies in the contact structure. Then theorem of Giroux that neighborhoods of two convex surfaces are contactomorphic if and only if there is a homomorphism between surfaces which okay. Okay, I should say some words, okay, about this definition. This definition is correct. In which sense? If we take some other vector field which is transverse to the surface and consider some other gamma, then this curve, this set of curves will be isotopic. There will be isotopic gamma is called dividing curve. Dividing curve is always transverse to the contact foliation. Consider a sphere, standard sphere, contact structure dz plus x dy minus y dx. Then the foliation will be like this. At the poles are singular points. Yes, if x and y are equal 0, then alpha is simply dz. Then dz is horizontal. Then these 2 points are singular. The foliation will be like this. Some curved meridians. And if you take some transverse vector field, then dividing curve will be just an equator. So this curve divides our surface into 2 parts, and this curve is always transverse to foliation. Okay, and now I will formulate the theorem. No, this is also embedded curve. This is a submanifold. Okay. All information about neighborhood of the convex surface is contained in the dividing curves. So, the theorem. Two neighborhoods are contactomorphic. If there exists a homeomorphism between surfaces, the image of one of the first dividing curve is the second dividing curve. So, two manifolds are called contactomorphic if there is a diffeomorphism between them, which sends the first contact structure to the second. So all information is contained in the dividing curves. This is a combinatorial data, so so we like it. Okay. We are interested in the classes of convex surfaces. Some contact surfaces, for example, take the standard contact structure. For example, this. This is an equivalent contact structure to one which I introduced in the beginning of the talk by some quadratic change of coordinates. So take this contact structure and try to find a disk, two-dimensional disk, which is embedded in the R3 and which is tangent to the contact structure on the boundary. D2 is tangent to contact structure at the boundary. Does there exist such disk or not? And for this contact structure, the answer is no. But if you take another contact structure, cosinus R dz plus R sinus R d theta. For such contact structure, there exists such disk. The picture, okay, just consider a horizontal disk of radius pi. Horizontal disk of radius pi. Yeah, if R equals pi, then this equals 0. So the contact structure is horizontal, so it is tangent to horizontal disk of radius pi. And this proves that two contact structures are not equivalent. They are different on R3. This is the note of Benneken, year 82 maybe. So the consideration of surfaces in the contact manifold is useful to distinguish two contact structures. And we aim to distinguish some Legendrian nodes using some similar considerations. So okay, now I will introduce rectangular surfaces for rectangular diagrams for convex surfaces. This is some combinatorial way to think about geometric objects such as convex surfaces and surfaces in general. Consider a torus, two-dimensional torus, with coordinates theta and phi. By a rectangle on two-dimensional torus, I mean the product of two segments of coordinate circles, theta and phi. For example, this is a rectangle, or this, or this. Here are three rectangles on this picture. The rectangular surface consists of rectangles. There are some restrictions. Rectangular surface, or rectangular diagram is a set of rectangles such that the intersection of two rectangles such that the intersection of two rectangles may be empty. It may be simply one vertex. One vertex may be two vertices, such as in the following picture. For example, such two rectangles have common two vertices. And they may have four common vertices. 1, 2, or 4 common vertices. And the last case, they may intersect like this. For example, which situation is forbidden? Such situation. If some vertex of rectangle lies in the interior of another rectangle, this situation is forbidden. For example, this is on the right a rectangular diagram of the surface. Rectangular diagram may have boundary surfaces. If a vertex of rectangle is not a vertex of any other rectangle, then call it boundary vertex. This vertex is a boundary vertex. If there is no other rectangle containing this vertex. Thank you. Boundary vertices are circles on this picture. This is the definition, but where are surfaces? I talk only of some rectangles on two-dimensional torus. So for every rectangle, we construct such tile. Consider S3 as a join of two circles, S theta and S phi. The coordinate on these circles. Then suppose this axis is theta, this is phi, this is the rectangle on the torus theta phi. And then we correspond to every rectangle R. A tile in the three sphere, which looks like such as in this picture. This is the graph of some function. Take some rectangle. Theta, phi. This function equals 0 on two opposite sides and 1 on the other two opposite sides. Here we have 0 and here we have 1. All these points lie on the circle of the join, and all these points are collapsed in one point. They collapse in one point, and you obtain a picture like this. So, the first picture is in coordinates theta, phi, tau, or the join. Yes? So, the join is the set of theta, phi, tau. Where theta belongs to S theta, phi, S phi, tau tau belongs to the segment 0, 1, and this set is factored modulo this relation theta phi 0 is equivalent to theta prime phi 0 for any theta and theta prime, and so in this picture these segments I collapse into one point on the circle of the join. And you see the sequence as one point. This, and this. Okay. So, in other words, we want that the projection of the tile to the torus theta phi is the initial rectangle. Projection theta phi of tile, of initial tile, that we construct, the tile that we construct is our rectangle on the torus. Also, our tile have vertices on the circles of the join. Tile is perpendicular to circles. You see here, tile is perpendicular. And when you move from one vertex to another, tile rotates somehow. So our surface is glued from mainly such tiles. For example, if you have non-intersecting tiles, then non-intersecting rectangles on the torus, then in the three sphere you get two non-intersecting tiles. So the surface is embedded. We want that the surface is embedded. If if two rectangles have one common vertex, when the picture is like this, and two tiles are glued into one smooth surface. Here we see the tangent plane, the common tangent plane, and the corresponding picture in the S3. If two rectangles, if the interiors are intersecting, then two tiles don't intersect, and you get this picture. So you obtain some surface in S3, and combinatorial restrictions on the rectangular diagram. These restrictions provide us an embedded surface in S3. The theorem is that this surface is automatically convex with respect to the contact structure, to the standard contact structure which I introduced in the beginning, and this contact structure in may be written in other coordinates like this. Cosinus squared p over 2 tau, where tau is the coordinate of the joint, d theta minus sinus squared p over 2 tau d phi. This formula simply means that when you move from this point of one circle to another, then the contact plane rotates. The contact plane is perpendicular to circles, and it rotates as this tile on this picture. So our tiles have some specific behavior related to our standard contract structure. Okay, the theorem is that every convex surface in S3 can be isotoped in the class of convex surfaces. Convex surface F, any convex surface. Can be isotoped in the class of convex surfaces to the convex surface which obtained from rectangular diagram to some the closed surface, you obtain a closed surface if there are no boundary vertices of your rectangular diagram. If any vertex of rectangle is a vertex of some another rectangle. To the convex surface obtained from rectangular diagram. Obtained from rectangular diagram. Okay. How many time I have? 5, 3. Okay. On this picture, you see on the left a trefoil, and on the right a Seifert surface for this trefoil. So now I want to formulate a result there is a problem. Suppose there are two links in contact manifold which are tangent to the contact structure. The velocity vector of each link lies in the contact plane. Such nodes, such links are called Legendrian links. This is the definition of Legendrian link. Okay, suppose you have two Legendrian links. The question is, provide an algorithm to distinguish these two links, two Legendrian links. Algorithm to distinguish L1 and L2 are called the same if there is an isotopy from L1 to L2 in the class of Legendre links. So if you can deform one Legendre link to another in the class of Legendre links, then they are called the same. So the question is to distinguish two Legendre links. This question is solved for topological nodes, but for Legendre nodes, the question is still open. And we provide some procedure to distinguish Legendre nodes. In this picture, there are two Legendre nodes. Okay. Each vertex of this picture, say theta 0, phi 0. For each vertex, it corresponds a segment in the S3. Take a point on one circle of the joint theta 0, another point on the another circle. This is S theta, S phi, phi 0, and this segment corresponds to this vertex. If on every horizontal and vertical line lies exactly 2 or 0 vertices, then the set of such segments for these all vertices, they are all glued in the link. And this is a Legendre link. As I said previously, it is obvious that this segment is tangent to this contact structure. So these are two links, and the question is, are they different or not? We can prove. Look at this picture patiently. Here we have a satellite node. There is a torus here. You see that contain two strands. This torus is not like a trefoil. This is some tiny torus in the sphere. And these torus have two dividing curves. Torus has two dividing curves. Which are noted as trefoil. Which are trefoils. But on the left picture, you don't see such a torus, and we can prove that there is no such torus on the left by some computer work, by considering all rectangular surfaces, all rectangular diagrams of surfaces in the complement of the link on the left. The beginning of this theorem is like this. So suppose there exists such torus, then by our theorem make it rectangular isotope in the class of convex surfaces. Then, by some simplification procedure, we can consider all cases and prove that there is no such torus, and prove that these two Legendre links are different. So, thank you.